Single clock synchronization circuits. We will see how we describe the combination logic and the sequential logic both at the same time. So especially we use the single clock. The single clock is applied and we have a flip-flop receive the clock, and the in between we have a logics, right? So we will see how we describe those kind of single clock synchronous circuits, and this will be very useful for all of you to design the digital circuits. For single clock synchronous circuit design, there's just something that you have to remember. The first is that no combinational cycle, meaning any combination logic, there's no feedback inside. Just the input goes in, the output goes out. If you have like a feedback circuit, some logic result will be feedback to the input like this. This cannot be considered as a combinational logic because it just keeps cycling inside the logic. So there should be no combinational cycles, and also single clock signal is shared among all the clocked devices like flip-flops. And also we only care about the value of the combination circuit just before rising edge of the clock, meaning after the input comes out of the flip-flop and all the value at the output through the combination logic, only the value at the output of the combination logic just before clock edge happen will be considered for the operation. So we only care just the value at the just before rising edge for this kind of rising edge flip-flops. Okay, and also period must be greater than every combination logic delay. So we have a clock here, the period here, any propagation delay TP1, TP2, here TP1 plus TP2 must be less than clock period T. This is very important. Some of the students, without having this kind of a notion, someone just designed the digital circuit, just period, the propagation delay exceeding the 1 clock period. In the simulation, it looks like working as you expected, but in real system, such a delay cannot be guaranteed. It will vary for different process voltage temperature. So you never use your propagation delay, never exceed 1 clock period. This must be a golden rule for single clock synchronous circuits. Okay. And also any change will save the state after node induced logic transition have stopped. So all the clean value will be stored, okay, on the flip-flop. So any glitches, so data going into flip-flop, we don't care. Only at the rising edge we catch this, right? The stabilized value will be sampled by the flip-flop. Okay, this is just example of the following logic Verilog description. So we define module on-off module. The input is clock and button. The output is light here. Since we are gonna use the light signal inside the always, we define that the rag in rag type. So this is rising edge flip-flop we are gonna define. So positive edge clock for the sensitivity list in the always statement. And if a button is high, the light goes to inversion of the light. It will invert the value. Otherwise, there's no definition, meaning it will keep its value. So here there's no else statement. It will be recommended you keep you complete the description, else the light just keep its value like this, right? Okay. So if you describe it like this, the synthesis will be synthesized like this. There's a multiplexer there. The multiplexer is quite useful for if statement. So if statement is satisfied, right, then it does the action on the right hand side, the description. So it flips the output by inversion, and they load that onto the flip-flop. Okay. Otherwise, if the button is low, it keep the value, right? Every cycle, it will keep the value. Okay. The input signal, button signal in the previous example, we are receiving that from off chip. The clock is running like this. That we don't know when this input signal will change, because this is not clocked by the flip-flop. It just is controlled by the human hand. So there's three cases. So what if the button signal comes to the flip-flop? It exactly align to the D. What will happen? First, it may miss the data. So the data Q will catch on the next rising edge, and the output will come out in the next clock. Another case is that this data change to the input flip-flop, so it will catch the data on the rising edge of the clock. So output comes out on that first cycle. So there's uncertainty whether the data will catch later or on this earlier, right? What if this input is exactly on the rising edge of the clock? So we cannot determine whether that is 1 or 0. Then the flip-flop output will go into metastable condition. Then the internal feedback back-to-back inverter try to hard resolve whether it is 1 or 0, right? It takes much longer time to settle. Finally, we cannot determine whether it will go up or go down. So this kind of a metastable condition will be problematic, because any logic after this event can fail, because the combination logic must complete within the clock 1 cycle. But having this kind of unexpected large delay will cause the system fail. So how we avoid this kind of the issue? So we know that this kind of input signal is called asynchronous signal, because we cannot determine the timing when this signal changes with respect to clock signal in our system. This is a very common problem for digital designer. So we have to reduce the failure probability. We'll see how we handle this kind of issues. Okay. Let's assume this condition that if we have a synchronous input and one flip-flop at the input, it goes into multiple combination logic and flip-flop after that in each. Once this one fail, all these paths will fail, right? TP1, TP2, and TP3, right? If this first flip-flop fail, all the paths will fail, right? But So we have to ensure that the chance of the failure will be minimized. If you have a multiple flip-flop at the input, this will make even situation worse, right? If this can fail, or so this can not, so one of those will be fail, and also any one of those may catch the value one cycle early or late. The timing all messed up, right? So we prefer to have only single flip-flop at the interface to make sure the timing is consistent for all the paths. But even with this kind of a single flip-flop system, we know that if this one fail, then all the paths will fail, right? Because the metastable happened, then the metastability happened, then we cannot guarantee the timing can meet define the clock period, right? So having single flip-flop will make the situation the less worse, but it cannot completely remove the issue. So what can we do, right? So to prevent the metastability, we add more flip-flop like this. If you add like this in the path, then the chance of them going into metastability will going down exponentially. So by the time we get to the last flip-flop, the output will be generated into a predetermined time, right? Even with this guy as metastable, by the time we have the next clock edge comes in for this second flip-flop, you may resolve the first flip-flop will resolve the output either 1 or 0, right? So this is kind of a standard way of avoiding such metastable issues, right? But we have to ignore the fact that this interface, the first flip-flop, is a asynchronous interface. We cannot eliminate the metastability. It is impossible to eliminate such a case. We have to admit that there's a chance, any chance of the metastability happen, right? So having multiple cascading the flip-flop, we will get the probability will goes down greatly. So solution is to, by adding more flip-flop in the path, we allow time for signal to stabilize. Okay. So now the question is, how many flip-flop we have to cascade, right? We need to consider clock speed and device speed, all these kind of things. So most of the common practice is the double synchronization. So we add at least 2 flip-flop in the path. So double synchronization. So add 2, at least 2 flip-flop on the asynchronous interface. Okay. In this chapter, we will see how we design finite state machine in Verilog. So finite state machine is a useful abstraction. For sequential circuit, we have indispensable elements like flip-flops and combination logic. For SSM, so we have the feedback. The one distinguished the feature is that combination logic output will goes into flip-flop, and the output of the flip-flop going back to the combination logic. This kind of feedback represent the states right? This internal stage plus an external input determines the output and next state, right? This is a very common representation of the finite state machine. So at each clock edge, the combination logic compute the outputs and the next state as a function of input and presented the stage. Okay. There are two types of a finite state machine. One is Moore and the other one is Mealy. The Moore is that the output is only determined by the flip-flop output like this, right? You know the hair condition like a moose. Moo only determines the output, only determines the stage, right? I remember this kind of relationship by thinking about the moose, right? The Moore machine only Moore machine's outputs are only determined by the state, right? But on the other hand, the Mealy machine, the outputs determined by stage as well as input, right? So there's a combination logic at the output can be, and the input directly feeds through to the last combination logic. This represents that even though the same state is here, depending on the input, the output will be different. But for the Moore machine, the output only determines by the stage, meaning even though the input changes here, if the input changes, if the input doesn't change the state, then output will be stays the same. So this is very to distinguish the structure for finite state machine design. You have to remember those two styles, and you have to use it with known knowledge. Without having this kind of concept, you will end up being like making a lot of the bug, or you cannot handle or manage your code, right? Typically, the Mealy machine is more compact, right? But it's hard to debug. So for Moore machine is more easier to understand, but more complex, more hardware resource, but easy to understand, right? We'll see some of the example. Let's take a look at an example of converting level to pulse. Right? So level to pulse converter can be used for the traffic signal for pedestrians. So on the right hand figure, if you push, then it generate the pulse. That pulse actually the only active for 1 clock period wide. Since we are pushing the button here, so it can come anytime regardless of the clock edge, right? So this is the synchronous interface inputs, right? So buttons and switches pressed by human for arbitrary period of time. So what we need to generate is a single cycle pulse for the counter. Okay, so we give it a signal, and the traffic signal turns on for some period of for a certain period of the time, the measuring by the counting the cycle. So let's say, for example, like 1,000 cycle, the traffic light goes blue, something like that. Okay. First, we can make the state transition diagram to implement this kind of a system. So first, we have that's 3 state. First state is the 0 state. So input is low and waiting for the input rise time. So the output P is 0. Once the input L here goes to high, then H is detected, right? If the input edge gets keep low, then we are staying at this stage. Once the rising edge 1, input goes to 0 to 1, then we detect edge detection state. We going into that state and then generating output pulse 1, and then immediately if the L is staying high, then we go to another state, high input but waiting for the fall, so output goes back to 0. So in this 1-2 transition generate the one single pulse, and then L is staying high, then we keep in this state, and once the L goes down, we're going back to the original state. So now the question is this kind of a state machine diagram, is this gonna be Moore or milli? Think about the output P. Does that depend on the input state? The state, we have a 3 state. Each state determines the output, right? If the state is 0, 0, the output is 0. If the state is 0, 1, output is 1. If the state is 1, 1, output is 0. So input is L here. Input L doesn't affect the output P. So this is Moore machine, right? This is Moore machine implementation. So in this case, at the input, we use the double synchronizer to eliminate the metastability issues. Okay, you have to use this synchronizer. Okay. Now the Moore machine, this is a typical block diagram of the Moore machine. We have the flip-flop generate the state. The state determines the output, right? So in this case, how we design this combination logic here, right? In P. So for combination logic design, we have to know the input here. The first combination logic receive the input L and also state, current state, right? S, current state and input. So the next one, we will receive the state input and then output. So for every state variable, depending on S0 and S1, we will determine the output P, right? For this kind of a Kano map, we have learned in the undergraduate course, the digital design. So we'll put all the cases of S and 0 and S1 in here, and then fill in the output cases. If the one is for the activating cases of the P, so activating P comes from this one, so that can be S0 is 0 and S1. S0 is 1 and S1 is 0. So these cases will generate. So the last output combination logic is simple to generate like this. How about the combination logic inside the state machine like here? So we first write down the input and an output conditions. The output of the inside the combination logic is the next state, S plus. So S plus is the next state and S is the current state, right? So next state is the output, right? So we go by looking at this state transition diagram. If the current state is 0, right, depending on 0 and 1 input, the next state is determined, right? So 0, next state is 0, 0, staying here. If the 1, they transition to next state 0, 1, right? The same way, if we have a 0, 1 state, then depending on the input, the next state is determined, right? we can fill in all these things, and then looking at this, we can optimize it to generate the output S plus. So S plus 1 plus can be L and S0, right? L is 1, so the case of the 1 is here, 1, 2. If you look at the two cases, when we generate this S1 plus is equal to 1, that one becomes 1 when, so L and S0, let's say L and S0 is 1, right? In these cases, we generate 1. If those two are, right, 1, 1, then S1 plus is 1. What about the S0 plus? For S0 plus, we have a here and here and here. The common thing is that only L is 1. Then we get that to S0 plus to 1, right? We can simplify the logic. I'm not going to repeat how we optimize this logic, right? We already learned that. So here, typically in Verilog we describe the behavior. This kind of a logic optimization will be done by the CAD tool. So normally what we need to do is just describing, just writing behavioral code. Alright, that will be enough for now. This kind of a logic optimization we just learned in the undergraduate courses for your practice, okay? Once we find the logic, combination logic on the same machine on the output side, then we implement that logic here and there, right? So we have a two flip-flop for generating S0 and S1, right? So it will come out like this, optimized down to this kind of logic. So in Verilog, what you have to do is you describe this combination logic here and describe the combination logic, the output, right? And define the flip-flop like this. So you have to remember this structure itself to describe that in Verilog. So you must understand this kind of structure, right? Really and more. Without knowing such concept, you cannot properly write the Verilog code. Okay. Now let's look at. So far, we just looked at the Moore machine. We will look at the Milli machine implementation as well. Let's implement our state machine using the Milli design in this time. So Milli, as you can see, we have a combination logic at the center for determining state, and also we have a output combination logic which not only take the state as well as it also take the input from direct feedback, right? So state machine becomes now simpler than the Moore machine because we only have, let's say, two states. In this stage there's no output here, right? The output only determined by the state and input. So from here, if the input is 0, we are staying in 0 here and then putting out the output 0. If the input goes 0 to 1 here, then output also specified p equal to 1, right? So input and state determines the output. Now if we go into the input high case state, while we are getting L equal to 1, we keep putting out P equals 0, and once the L goes down again, the P equals to 0. So here, what is important, the critical, major difference from the Moore machine is that in Milli machine, whenever the input changes, the output immediately affected, right? The output transition immediately whenever the input changes. For this kind of state machine is widely used for having very low latency. I mean, if you need to respond to the input event quickly, then you have to use Milli machine. For example, you are working at the nuclear plants. Something bad thing happened in the nuclear plants. once the event is detected, the measurement, the output measure, you need to react at that moment quickly, right? For this kind of emergency system, you need to use a milling machine. If you were to use the Moore machine for any input changes, for example, nuclear plant is about to explode, but so the shutting down the nuclear plants, it will happen at one cycle later if you are using Moore machine, right? Because after state transition happen, the output will changes, right? So this kind of emergency state situation, you need to use a milling machine so that the output affected immediately, okay? Now the milling machine logic can be optimized by having this kind of a state machine, current state and inputs that will determine the output state, right? And the output as well, right? P. So we generate those things and optimize logic. You will get this kind of a synthesis result. So the input directly go to the output. So the state actually determines the state and the input determines the output. So this milling machine to simplify the circuits, but it is very difficult to understand or interpret this kind of a system, right? So this is so optimized, so compact design. So this will be difficult to debug when there's something is wrong or error is there. It's difficult to identify what is wrong here, okay? But having milling machine, we have a more compact design, and also the immediate response to the input changes can be achieved, okay? Now that we can compare the Moore and milling machine trade-off, how are they different? So Moore machine, you know, the output is only determined by the state. But the milling machine state and input will determine the output. So milling output generally occur one cycle earlier than Moore machine, right? The output immediately changes for the input, but for Moore machine, the output comes out one cycle later. Okay? So milling, most of the time, difficult to conceptualize and design because it's so compact and optimized the design. So and also have pure stage, okay? So I would recommend for you guys, if you need to design Moore machine, typically try to implement that in Moore machine style because that will be much simpler to understand and implement. But if the system requires a more faster response or less delay, then we consider the milling machine design topology. Okay, so here logic, flip-flop, output, right? Output logic. This one is the Moore machine, right? If something is urgent need or care must be taken, then take the state as an input and also input to there, right? Like this. So starting from Moore machine to milling machine, it is easier, right? It will be easier transition because we have a more state inside defined, right? We can do more things. But if you are starting with the milling machine style, like first, then it will be difficult to expand it to the Moore machine style because the milling machine has a fewer stage, right? Difficult to conceptualize. So normally it will be a bad idea of transitioning from milli to more, right? So I would recommend you guys to start with the more machine, and then if you really need faster response for urgent need, then you consider milli by adding some the path there. Okay.